Hello, this is Dr. Armand again, giving you another fantastic lecture on um, acids. And today we'll be talking about very simply the fundamentals of organic acids. We'll kind of cover how to name them, how acids are named, and how we can determine, what enhances the strength of an acid. So again, an acid is strength is based on how easy it can give up its acidic proton. So we're going to be talking about some of the characteristics of organic acids that they can have to enhance their acidity of the acid. So on that note, sit back, relax, and let the chemistry flow. So this is part 2 of the acid lecture. Oopsie doopsie. So let's get started. First, we're going to talk about how do we name organic acids, and it's very similar to naming alkanes. You remember we talked about, maybe you did in Gen Chem 1, alkanes, methane, ethane, propane, butane, hexane, heptane, pentane, pentene, pentyne, etc. And so when naming organic acids is pretty much the same way, except instead of using the ane, ene, or ine as the ending, we use the ic. The ic symbolizes it's an acid. And so we still use the same numbering prefixes that we use for alkanes, alkenes, and alkynes. And so here we have this acid. So we count the number of carbons. It has 1. So we use the prefix meth. It's an acid, so we use oic. So this is methanoic acid, commonly referred to as formic acid. So methanoic acid tells you it has 1 carbon in that acid. The oic tells you it's an acid. We go to the second one. We have, starting with the one that's attached to the oxygens, we have 1, 2. So we use the prefix eth. So it becomes ethanoic acid. Etha meaning 2 carbons, noic, or ic, oic, representing the acid. So ethan, oic. Ethanoic, ethane, comes from the ethane meaning 2, or comes from the eth prefix meaning 2. And actually, my bad, we got to correct something. Methanoic acid. So meth comes from the, let's repeat, we'll start over, my bad. I forgot something. So we'll start back at methanoic acid. So meth refers to the number of carbons and refers to the type of bonds between the carbons. So since there's only 1, it's a single bond. Oic makes it an acid. So this is a acid with 1 carbon, single bond, so methanoic acid. Here we have 1, 2 carbons. So again, the prefix eth and refers to there's only a single bond connecting the 2 carbons. And then oic is acid. So ethanoic acid is referred to as acetic acid. So ethanoic acid is the systematic name, whereas acetic acid is its common name. Next, we have an acid with 3 carbons. So we use the prefix prop. And these carbons are connected by single bonds. So we use the root and then the ending oic. So propanoic acid. Now, if we have these 3 carbons and at the end we put a double bond, notice the change in the name. It becomes propenoic acid. Ene meaning there's a double bond somewhere in that carbon chain. So ethanoic acid can only be ethanoic acid. You can't have ethenoic acid, because then what will happen is carbon that's attached to the carboxylate would have more than 4 bonds, and that's a no-no. So propenoic acid means we have 3 carbons. There's 1 double bond in that compound, and since there's only one place you can put the double bond, you don't have to put the number. And then oic refers to acid, and this is called acrylic acid, the common name. Now, in some cases, here in the next example, we have 2 carboxylate groups. Just trying to show you all the different, things that go into naming acids. But these 2 carboxylate groups are still connected by 3 carbons. So we still use the prefix prop. And since those 3 carbons are connected by single bonds, we use the same ending ane. Now, since there's 2 carboxylic acids, we use the ending dioic. So this is propane dioic acid. So propane meaning the 3 carbons are connected by single bonds. Dioic means there's 2 carboxylate groups on the acid. And this is commonly referred to as malonic acid. Next we have starting from the carboxylate 1, 2, 3, 4 carbons. So we use the prefix bute. And these 4 carbons are all held together by single bonds. So we use the root ane, and then since it's an acid because it has 1 carboxylate group, oic. So this is butanoic acid, commonly referred to as butyric acid. Next, again, we still have a compound or an acid with 4 carbons, but notice after the second carbon, we have a double bond. So we still have bute, meaning 4, ene, or butene, ene, meaning double, oic, meaning acid. This is butanoic, but we have to include the number after which the double bond comes after, because it can come after the second carbon or it could come after the third carbon. And so this one comes after what? That's correct, the second carbon. So this is called 2-butanoic acid. And by the way, you always start with the carbon on the carboxylate group. So it goes 1 and then 2, and then 2 is the double bond. This is commonly referred to as crotanoic acid. Now here between these, on the last example, we have 4 carbons all connected with single bonds. So we have butane, and since there's 2 carboxylate groups, it becomes dioic, and this is referred to as succinic acid. So again, we just want to introduce some of the basic naming rules for naming acids. So again, it's pretty much similar. We use the prefixes meth, s, pro, bute, all the way up to normal ones. If they're all single bonds, we use an. If it's double bond, ene. Triple bond, you'll learn about that in organic. And then we use the ending ic to represent acid. If it has 2 carboxylate groups, we'd use dioic instead of oic. So let's move on. So here we have this acid, and we want to name this acid. So the first thing you should do is count the number of carbons in the longest chain. First, so let's do that. So we got 1, 2, 3, 4, 5, 6. So we got 6 carbons. So we're going to be using hex. So all the ones that don't have hex in it, we can get rid of. So we can get rid of B. It doesn't have hex in the name. We can get rid of C. It doesn't have hex in the name. We can get rid of F. It doesn't have hex in the name. Now, does this compound only contain carbon-carbon single bonds? Well, no. It has a double bond here. So now we have to use the root En. So we got hexene. So we look at hex. If it has an ene, we keep it. If it doesn't, we get rid of it. So this one has hex with the en, we keep it. This one has hex with a yn, we drop it, because that doesn't mean double bond. We have hex with an en, we keep it, and then hex with en. So we narrowed it down to 3. And since it's only got one carboxylate group, we just use oic. So far we have hexanoic acid. But we're not finished. We're not finished. Since we have more than 3 carbons, we have to include the carbon after which double bond comes after. And so if we start here, 1, 2. So it comes after the second carbon. So we should write this as 2-hexanoic acid. Now, we would stop there, but however, we have one more substituent, the chlorine. And chlorine comes after which carbon? When we start again from the carboxylate, we go 1, 2, 3, 4, 5. So when we write this, we would write it as 5-chloro-2-hexenoic acid, which would be G. G is the correct answer because it's 5-chloro-2-hexenoic acid. Again, you always start counting from the carbon attached in the carboxylate group. That's your number 1 carbon. 1, 2, 3, 4, 5, 6. All right. Let's clear this out. Now we have this acid. Something other than green. I get tired looking at green. So again, the first thing we need to do is count the number of carbons. So we got 1, 2, 3, 4, 5. So we know the root's going to have pen. So anything that doesn't have pen in it, we get rid of it. So we can get rid of A, E, F, and I. Now, are there any so now we got to look at it. So we determined the number of carbons. It had 5, so we're going to use pent. Now, does it have any double bonds? The answer is yes. So what is it after? So we got 1, 2, 3, 4. So it's after the 4th carbon. So the way we would write this is 4-pentanoic acid. And that would be answer choice B. Now let's get into some of the physical properties of organic acids. And so here there's a good statement that says the melting points and boiling points of carboxylic acids are higher than those of hydrocarbons and oxygen-containing organic compounds of comparable size and shape. So what does that mean? That means if you're comparing a carboxylic acid with other compounds with similar size, aka similar molar masses, then the carboxylic acids are going to have a higher melting and boiling points. And this is due to the strong intermolecular forces. So for example, when we look at 2-methyl-1-butene, what type of intermolecular force does this compound have? That's correct. Dispersion, because it's all nonpolar. Now we go to 2-butanone. So we replace that double bond with a double bond oxygen. So what kinds of intermolecular forces does this compound have now? That's correct. Dipole, dipole. This has a dipole now. And notice the increase in the boiling point. We went from nonpolar to polar. We increased the boiling point. Now if we look at 2-butanol, we replace that ketone with an alcohol. So now what type of intermolecular forces do we have? That's correct. We have hydrogen bonding. And so you see again an increase in the boiling point because hydrogen bonding is stronger than dipole-dipole. Now we get to propanoic acid. So again, we have an OH, which is hydrogen bonding, but we also have a double bond oxygen, which is dipole-dipole. So together, these enhance the intermolecular forces for carboxylic acid. Again, we're comparing apples and apples, not apples and oranges. So why is this carboxylic acid? What's so unique about it is that when it interacts, it forms what's called these dimers. So the OH on one carboxylic group, hydrogen bonds with a carbon double bond oxygen on another, and then that carbon double bond oxygen interacts with the OH on another carboxylic. So it forms this tight interaction between the two. And since it's very tight, it's a very strong intermolecular force. This is a very common interaction with carboxylic acids. I mean, this is probably the most common thing carboxylic acids do is they form these hydrogen bonded dimers. That's what it's called. Hydrogen bonded dimers, and you can use X-ray crystallography to actually see the actual dimer and measure the distance between them. So the closer the two atoms are, the stronger the hydrogen bond is. The further apart, the weaker it is. And there's things you can add to acids to enhance its intermolecular forces. And again, we study this using X-ray crystallography, the distance between the O and the H, the hydrogen bond distance. So here we're looking at this series of compounds. We want to know which one have the strongest intermolecular force. So what we're looking for first is which ones are polar, nonpolar. So let's go through it. So is A polar or nonpolar? That's correct. It's nonpolar. So let's go ahead and mark that one off. And again, these are all of comparable sizes. Next we have orthochlorobenzoic acid. Is that polar or nonpolar? That's correct. It's polar. What about parafluorobenzoic acid? Polar or nonpolar? That's correct. It's polar. What about D? Polar or nonpolar? That's correct. It's polar. And what about E? Polar or nonpolar? It's polar. Now here, we want to see which one have the strongest intermolecular forces. So what we can do is, there's actually two different categories of compounds here. So B, since it has a chlorine, and E has an OH. F has a fluorine. So all of these have additional substituents on it. So we know that one of these three is going to be the strongest. So we can knock off benzoic acid because it doesn't have any substituents on it to enhance its intermolecular forces. So now we got chlorine, fluorine, and we have a hydroxyl. Now, B and E, these substituents are closer to the OH. F is further away. But between Cl and OH and F, OH is a hydrogen bonding group. So E is going to have the strongest intermolecular forces because it has the ability to hydrogen bond with the carboxylate part and the OH part, whereas the others can only have enhanced dipole-dipole in addition to the hydrogen bond part. So E is the answer. So which would exhibit the highest melting point? So which one of these has the strongest intermolecular forces? So let's look at this. Is it A? What type of intermolecular forces A have? That's right, it's non-polar. So it's definitely not A. What about B? Which type of intermolecular force does it have? That's right, it's polar. So it'd be dipole, dipole. That could be one. What about C? What type of compound is that? That's right, it's a carboxylic acid. So it has hydrogen bonding and dipole, dipole. What about D? What type of compound is that? I'm waiting. I'm waiting. That's correct. It's a ionic compound because it has lithium in it. So this lithium is a metal. So when you have a metal and a non-metal, you have an ionic compound. And then E, we have an OH group. So we have hydrogen bonding. So which one would have the highest melting point? Again, these are comparable sizes. This would be D because D is an ionic compound, very strong. Forces hold it together. So this would be lithium pentonate. And so anytime you see a metal attached to the oxygen, that's the cation anion. That's going to be ionic compound. And that's one of the most common things students miss whenever I talk to organic professors is they don't understand that when you have a metal attached to a non-metal, it's a salt, ionic compound. So let's talk about how does a carboxylic acid get its acidity? And so we always say that carboxylic acids are acidic because they have carbon, hydrogen, and oxygen for the main and the carboxylic group. And so we say that it's much stronger than waters or alcohols, but alcohol also has carbon, hydrogen, and oxygen. And alcohol also has a hydrogen attached to an oxygen. So what makes a carboxylic acid a lot more acidic than an alcohol? First off, if we just look at what's called the pKa, which is the strength of an acid, the lower the pKa, the stronger the acid. The pKa of ethanol is 16, which means it's very unlikely it likes to give up its hydrogen. And so ethoxide ion is a strong base. And ethanol is a very weak acid. So the Kc for this is going to be very low. It's going to be less than 1. And this tells you that ethanol doesn't like to give up its hydrogen. And you see here that delta G is positive. We'll learn more about that later, but when delta G is positive, it means something is non-spontaneous. It takes energy for it to happen. So this is delta G positive 91. It takes a lot of energy. So the ionization of ethanol is not, it doesn't really like to ionize ethanol. So very pK 16. I mean, means you need to get a pH scale only goes up to 14. So you're never going to, I mean, in very rare circumstances, ionize ethanol. Now, if you have ethoxide, it can go and scavenge for a proton and form ethanol. That's not a problem. Ethoxide is a very strong base. Remember, it always goes from strong to weak. Now we have ionization of acetic acid. And by the way, since ethoxide is a very strong base, it's a very unstable species. It's looking for a proton because it's very unstable, very reactive. It wants to get a proton and form ethanol, which is weak, a weak acid. So here when acetic acid ionizes, we form the acetate ion, and we see that the pK is 4.7. So this is a weak acid, but it's still relatively, strong weak acid compared to, for example, ethanol. So it doesn't mind giving up its proton because the pK is around 4.7, and the delta G is lower. But since delta G is still non-spontaneous, it prefers the Kc less than 1. But it's easier to ionize acetic acid versus ethanol. And why is that? Why is it easier to ionize acetic acid versus ethanol? And for example, since acetic acid is a stronger acid than ethanol, acetate is a weaker base than ethoxide because acetic acid is stronger. That means its conjugate base is going to be weaker. And so you may say, well, both can be stabilized by solvation. So when they're put into the solvent, they're stabilized. But you'll see here that the acetate ion has greater stabilization than the ethoxide ion. And in addition to being stabilized by the solvation, acetate has 2 additional avenues of stabilization that ethanol does not. And this is typical for all carboxylic acids. Carboxylic acids will have 2 additional avenues of stabilization that alcohols do not. So if you're falling asleep now, wake up. This is important. This is like the core of this lecture. Why carboxylic acid is more acidic than alcohols. It's these 2 additional avenues. These are very important avenues to remember. So, what are these 2 avenues? So again, these are 2 things that carboxylic acids have that alcohols do not. So in this case, the acetate ion has, the alcohol does not. So the first one is called the inductive effect of the carbonyl group. Because remember, the carbonyl group is polar and it's electron withdrawing. And this is a term you're going to hear quite often. So what does electron withdrawing mean? It means it removes electrons, it removes electron density from the reaction center. So here, this carbonyl is polar. It's removing electron density from the reaction center, making this oxygen here less negative. So when something is less negative, it's more stable. It's not going around, acetate's not going around looking for a proton. It's less negative. It's not as attracted to a proton as it once was. So this inductive effect, this ability of the carbonyl group to pull electron density, we're talking about electron density, I'll do ED for short, electron density away from the reaction center. So for a conjugate, for an acid, the reaction center is the OH. So for a conjugate base, the reaction center is this single bond oxygen. So if we remove electron density away from that single bond oxygen, we make it less attractive to these protons that are floating around. So since it's less attractive, it's a more stable conjugate base because it's less attractive to the protons floating around. However, for Ethanol, or the ethoxide ion, it has no inductive effect. So it has its full negativity, if that's a word, on the oxygen. So it's looking around, it's like a radar looking for protons. As soon as it finds a proton, because it's so unstable, highly reactive, that it's going to form the alcohol. So this is one reason why carboxylic acids are more acidic than alcohols, because it has this inductive effect. It stabilizes the conjugate base. So it's not just so negative, it's hunting for protons. Whereas the alcohol has no inductive effect. So the oxygen is very negative. It's like, hey man, I want a proton. It's looking around, scavenging for protons. As soon as it finds one, bam, it's going to form alcohol. Whereas acetate's kind of lazy. He's like, man, I'm okay. I don't need any oxygen around. I don't need any hydrogen. I'm not that negative. I'm chilling with my friend over here, the carbonyl. So that's one thing, the inductive effect. Carbonyl group, remember this is electron withdrawing, meaning it removes electron density between the carbon single bond oxygen, making the oxygen not as negative. The other thing that affects the acidity, or why affects, or another thing that helps enhances the acidity of carboxylic acids, is the resonance effect. And this may, hopefully you remember this from last semester, but resonance effect is when the double bond can alternate between multiple positions. And so with a carboxylic acid, you always have this resonance effect. And why is the resonance effect important? The reason it's important is because it can, let's see, what's the word? It can minimize the effect of the negative charge, because the negative charge always is flipping back and forth between the two oxygens. So since there's a resonance, that means this oxygen is not fully -1. It flips back and forth, so about half the time it's a negative charge, the other half it's not. So it has an overall charge of about -1/2. And so this resonance helps spread out the negative charge on the oxygen. So there's not one oxygen with all the negativity on it. So you have this flipping back and forth, which spreads out the charge. But alcohols do not have resonance. So since alcohols do not have resonance, they can't spread out the negativity. So again, that alcohol, when it's an alkoxide, is very negative. It's just hunting for a proton. Whereas the acetate or carboxylates, when they give up, in their conjugate base, they have this resonance. That negative charge is spread out. They're not as negative. They're laying back. They're not too eager to go get a proton. And this is just showing you how that negativity is evened out. So for ethoxide, you have this big red area of electron density. That means that oxygen is super negative. It's just waiting, hunting, like a shark looking for fish. It's hungry. It wants a proton. But over here, this acetate group, you see the electron density is more evenly spread. So not one oxygen has all the negativity. So they're kind of relaxed. They're not as anxious to get a proton. But they will if the conditions are right, but they're not like super hungry for protons. And again, that's due to in addition to the inductive effect, also the resonance effect. They work together. And you can tell that the resonance effect is occurring because if you measure the bond distances, so a typical carbon double bond oxygen is about 121 picometers. A carbon single bond oxygen is 136, but for the acetate, the bond distance is about 125, which is somewhere between a double and a single bond. So that tells you that the resonance is occurring. So why are carboxylic acids more acidic than their alcohol counterparts? Is because they have the inductive effect from the polar carbonyl group, which is C double bond O, and from the resonance effect. Because carbonyl groups are electron withdrawing. They remove electron density from the reaction center, which is the oxygen with a negative charge. On the other hand, resonance helps too, because resonance helps spread out any negative charge that oxygen would have between the two oxygens. And so that's why carboxylic acids are more acidic than their alcohol counterparts. So there are different things. So you can kind of think of organic acids as Mr. Potato Heads, because you can add different things to the acid to either enhance or not enhance the acid. Kind of like you can add ears to Mr. Potato Head, you can add a nose, you can add shoes, mustache, and if you have Mrs. Potato Head, you can add things to her as well. Organic acids are like that. You can modify acids and affect its acidity. So one thing we can have added to acids is we can add alkyl groups. And alkyl groups, of course, are nonpolar groups. Since they're nonpolar, they can't really polarize the OH bond. And alkyl groups are commonly referred to as electron donating groups. So instead of withdrawing electron density from the reaction center, it's actually pumping electron density into the reaction center. So it doesn't have any major effect on the acidity, but in some cases you could actually see if you have enough electron donating power, you could see the acidity slightly increase. Because again, alkyl groups are commonly referred to electron donating. They're pumping electron density into that reaction center. So for example, formic acid was just one carbon, two oxygens, and two hydrogens. But when we add a methyl group, now we're adding a little bit of electron density to it. Or no, we're adding a nonpolar group. But that methyl group can't remove electron density away from that reaction center because it's nonpolar. If anything, the opposite happens, and since it's electron donating, it's actually making the acid weaker by adding the methyl group. So what happens is when we have formic acid, pKa is 3.75. So again, the lower the pKa, the stronger the acid. When we put a methyl group on it, such as in acetic acid, it becomes 4.7. So what happens? So what happens is when the pKa goes up, it's harder for this hydrogen to leave. And so what's happening is this oxygen is holding on tighter to that hydrogen, making it harder to remove. So when we add another carbon alkyl group to it, now we have propanoic acid, we get 4.9. Not much change in it. When we add two groups, we get 4.8. So again, there's kind of a leveling effect with alkyl groups. When we added the first one, bam, it was almost a 1 pH difference in the pKa. But we add 2 or 3 to it, or 1 or 2 to it, not much difference. But now when we add 4, so we add this big bulky T-butyl group, we see at least a modest increase in pK, but not much. I mean, from 4.7 to 5.1, it's not that much difference. But the main difference is when we go from formic acid to acetic acid, we see a big difference in the pKa. So again, alkyl groups are called electron donating. Donating groups, what happens is they push electron density into the reaction center, causing that oxygen to be more negative, holding on to that hydrogen a little bit tighter, so it's harder for it to dissociate or ionize. If it's harder to ionize, it's not a strong acid. So what else can we have added to acids to affect its strength? And so what we can add to acids, and this is very important, is that we can add electron withdrawing groups. So these are groups that withdraw electron density away from the reaction center. And you may ask, for a carboxylic acid, what is the reaction center? The reaction center is that OH bond. So if you can remove electron density away from that reaction center, the hydrogen is less likely to remain, because now oxygen is not looking very attractive. It's getting rid of its negativity. So hydrogen will leave. So the easier that hydrogen can leave, the stronger the acid is. So again, what we're looking at is this. This is the reaction center of a carboxylic acid. And so the more electron density you remove from that reaction center, the easier it is for this hydrogen to pop off. So the easier it is the hydrogen to pop off, the stronger the acid is. So it's a stronger acid, meaning it has a more stable conjugate base. So that hydrogen's ready to go pop. It's off. It doesn't like oxygen no more. And so some strong electron withdrawing groups are things like halogens, so group 17 elements. You add those, it increases the acidity. Haloalkyl groups. So what's a haloalkyl group? For example, if we have a carbon, methyl, it looks like this. That's methyl group. Trifluoromethyl would look like this. So this is a haloalkyl group. This would, for example, 3 fluorines on the group. So again, this is attached to the rest of the molecule. So that's what a haloalkyl group is. Nitrils are carbon triple bond nitrogen. Of course, we already mentioned carbonyls are electron withdrawing, and nitro groups are electron withdrawing. Out of all of these groups, the nitro group is the strongest electron withdrawing group shown here. And again, all of these electron withdrawing groups help destabilize the electron density around the OH bond. If you destabilize it, you make the hydrogen easier to remove. Easier. So something is easier, it's a stronger acid because that hydrogen just pops off. And so you see here, electron withdrawing groups for halogens, we usually look at electronegativity. So fluorine is the most electronegative of the halogens. So we have fluoroacetic acid. So what does fluoroacetic acid look like? If I can draw it. Oh. And again, when we're comparing apples and apples because it can get kind of complicated kind of fast. So acetic acid is this. Fluoroacetic acid looks like that. So again, this fluorine does a good job of removing electron density. Because if you remember, acetic acid's pKa was 4.7. So we went from 4.7 to 2.6 just by adding a fluorine group to acetic acid. Now, chlorine is less electronegative than fluorine, so it has less of the ability to withdraw electron density from it. So it gives a pKa about 2.9. The same for bromine, and of course, iodine. Now, if you add more than one group to the acid, so say instead of adding 1 halogen, you added, for example, 2 halogens or 3 halogens. That has a significant impact on the electron withdrawing ability. So here let's look at chloroacetic acid. So that's chloroacetic acid. Let me finish. It's got a chlorine here. Sorry, it's a little messy, but it's just 1 chlorine. So chloroacetic acid, excuse me, 2.9. Now let's look at dichloroacetic acid. What did we do? We just added another chlorine to it. We enhanced the electron withdrawing effect on the acid. So now we have 2 chlorines. We went from 2.9 to 1.3. So just by adding an extra withdrawing group, we can remove a lot of electron density away from that reaction center. So remember, this is removing, and so since we added 2, we get a lot of electron density being removed. Now let's say we want to add 3 chlorine groups. Again, you have resonance on top of this. That's removing electron density. 1, 2, 3. And so now you have 3 electron groups, 3 electron withdrawing groups. Now trichloroacetic acid is 0.9 compared to 1.3 with dichloroacetic acid, and then chloroacetic acid was 2.9. So you're removing a lot of electron density away from that reaction center, making it easier for the hydrogen or the proton to be removed. And if you make it easier for the proton to be removed, that means that you have a stronger acid and a more stable conjugate base. Because now that conjugate base is like, I'm not too interested in finding a proton. I'm okay. So it's more stable. It's not as reactive. And the last thing I want to mention is the closer the electron withdrawing group is to the reaction center, the greater the effect. So here we have 2-chloroacetic acid, 3-chloroacetic acid, excuse me, not acetic, 2-chlorobutanoic acid, 3-chlorobutanoic acid, and 4-chlorobutanoic acid. And you see the closer the electron withdrawing group is to the reaction center, the greater the electron withdrawing ability is. So we go from when it's 2-chlorobutanoic acid, pKa 2.8. 3-chlorobutanoic acid, pKa 4.1. So you're the further away from the reaction center, you kind of you're kind of minimizing the effect the electron withdrawing group has. And then 4-chloro is 4.5. Key things here, comparing apples and apples. The stronger electron withdrawing group removes more electron density from the reaction center, causing the pKa to decrease when comparing the acid without the electron withdrawing group. Second is the more electron withdrawing groups you add, for example, the halogens, the more halogens we add to it, the greater we enhance the acidity, making it easier for the proton to remove. And then third is the distance away from the reaction center. So the closer the electron withdrawing group is to the reaction center, the more enhanced the effect will be. Again, these are just very basic things, basic principles that we're talking with very straightforward acids. When you go to organic chemistry, these things may change based on the change in the simplistic nature of the acid. We're only looking at, again, apples and apples. You know, we're not comparing very complex things, just very simple systems that we can look at and identify which one is the stronger acid. Other types of electron withdrawing groups. So if we look at, for example, methoxy, alkoxy groups, cyano, and nitro. So nitroacetic acid is 1.7. So remember here, fluoroacetic acid was 2.6. So if we're comparing fluoroacetic acid with nitroacetic acid, it's going to have a lower pKa, thus a stronger acid. And the reason is because within the nitro group, you have resonance in addition to being, you know, the nitrogen oxygen double bond. So you have a lot of electron density being withdrawn from the reaction center. Cyano group, not as strong as the nitro group, but it still has a good electron withdrawing ability. So 2.5, if we look at fluoroacetic acid, was 2.6. So cyano is comparable to fluoro. And then methoxy doesn't have much of an effect. I mean, it has some electron withdrawing ability because, again, acetic acid is 4.7. So with methoxy, it's 3.6, but it's not as strong as the halogens. So if you look back, I mean, even with iodoacetic acid, it was 3.1. With methoxyacetic acid, it's 3.6. So it has some, you know, it enhances the acidity a little bit, but it's not as strong electron withdrawing group as the halogens. So if I was to, you know, kind of scale these, I would say nitro, of course, the strongest electron withdrawing group out of what we've given. Then the cyano and fluorine, probably about the same gauge. It depends. And then the other halogens, and then we have the methoxy. And carbonyls is somewhere floating around in there. So again, we're just going to be comparing simple systems, apples to apples. So just wanted to show you with benzoic acid. Of course, benzoic acid is a carboxylic group attached to the benzene ring. And if you see down here, acetic acid is 4.7, acrylic acid is 4.3, benzoic acid is 4.2. And the reason that acrylic and benzoic acid are more acidic than acetic acid is because there's additional resonance that can happen. And the same for acrylic acid. Since you have more resonance, you can spread out the charge more, so the pKa goes down. And so you don't have to remember this. I mean, you don't have to, it's not like you're going to be examined over this, but here's just showing you how the resonance structure in benzoic acid happens. So this is the normal, what we draw, but then what happens is you can resonate the double bond here, and then also you can resonate it here. So it just resonates around the ring. And so the resonance structure of benzoic acid would look like this. So you can really spread out the electron charge. Now here for benzoic acid, say this is our main group. The position of 1, 2, and 3 gives you the ortho, meta, and para position. So when another group is at 1, it's called ortho. When the group is at 2, it's called meta, and when the group's at 3, it's called para. Now with benzoic acids and their derivatives, it gets kind of hairy kind of quick. So we're only going to be looking at very simple systems. Again, apples to apples, we're comparing acid strength. So for example, benzoic acid we would look at, and then I might say, okay, compared to benzoic acid, which one would be more acidic? Benzoic acid or parafluorobenzoic acid? You should know, okay, fluorine's electron withdrawing, so it would make it more acidic than just benzoic acid. So very simple, straightforward comparisons, just so you get the understanding of how electron withdrawing groups behave. So here we're looking at which one of these would have the strongest intermolecular force. Oh, we already did this one, my bad. We'll move on to the next question. So what's the name of the following acid? So again, our carboxylic group is here. It's attached to a benzene ring, so this is the root is benzoic acid. Now, in the I made a boo-boo. Yeah, the second, excuse me, so if we make this number 1, this number 2, this number 3, and this number 4, then this is the, if it's in the second position, I apologize, on the last slide I said number 2 was actually number 1, but it's what I meant is it's 1 away from the main group, which is on carbon number 2. It's ortho. If it's 2 positions away from the main reaction group, or it's on the, which is the third carbon, it's meta. And when it's 3 positions away from the main group, which is the fourth carbon, it's para. So hopefully you make that note in your notes. Actually, carbon 1 is on the main group, and then 2 is ortho, 3 is meta, 4 is para. And 4 means it's 3 away from the main group. And so this would be meta-chloro benzoic acid. So again, if I go back just to kind of clarify, not that one, this one. So meta would be, we call it the second carbon is ortho. Meta is the third carbon, and para is the fourth carbon from the main group. So this is 1. So once we identify 1, then we can do para, meta, ortho, meta, and para. Very simple systems. We're not going to get too bogged down in benzoic, because that's like a can of worms that you'll learn about in organic chemistry. So here we have this reaction. We want to predict the value of Kc in this. So when we look at this, we need to determine which side has the stronger acid, because it's always going to go from strong to weak. And so I give you the in this case, I give you the pKa's. I say the pKa of ammonium ion is 9.3. The pKa of benzoic acid is 4.2. So since benzoic acid has a higher pKa than ammonium cation, then the net reaction goes to the left. So here Kc would be less than 1. Also, you can note that the hydrogen here is attached to a nitrogen. The acidic proton here is attached to an oxygen. And since oxygen and nitrogen are in the same period, you look at the one that's more electronegative. So since oxygen is more electronegative, it's going to be the stronger acid. So now we're comparing these two. So we have two acids. We want to determine which one is the stronger acid. So here we have the acidic proton attached to an OH, acidic proton attached to an OH. Both of them have resonance because they have a carbonyl, and both of them have electron withdrawing groups. Here we have to decide which one is the stronger electron withdrawing group. And hopefully you paid attention, because I did mention this. And I said that the cyano group is comparable to fluorine. So that would mean that this one is a stronger electron withdrawing group. It would be the stronger acid because it can remove more electron density away from the reaction center. Here we have two groups. Again, both of them have the acidic proton attached to an oxygen, so we can't make any distinguished comparison there. Both of them have resonance, so nothing distinguished. Everything's equal. Now we see that this one has an electron withdrawing group. This one has an electron donating group that has these alkyl groups. So again, electron donating means it's kind of pumping electron density back into the reaction center. That's what we don't want for an acid. We want to remove electron density away from the reaction center. And so this one is removing electron density away from the reaction center. So since this one's electron withdrawing, this one would be the stronger acid. Stronger meaning it's easier to pop off the acidic proton, and the conjugate base is more stable. So now here's a different take. And in this question, we want to know which of the following would have the stronger conjugate base. So we're not looking for stronger acid, we're looking for stronger conjugate base. And what you have to remember here is stronger conjugate base equals weaker acid. So the weaker acid would have the stronger conjugate base. So now we want to look to see which one is the weaker acid so we can determine which one is the stronger conjugate base. So again, they both have the acidic proton attached to the oxygen. We both have resonance, so no change there. This one has a methyl group. This one has a fluoro group. Because the fluorine is more electron withdrawing, it's going to remove more electron density away from the reaction center, whereas the methyl group not going to do much, maybe even pump a little bit of electron density back into the reaction center. So this is the stronger acid. So then this would be the stronger conjugate base. You got to think opposite. So the weaker acid is the stronger conjugate base. The weaker conjugate base is the stronger acid. Wait, yes. Yes, because stronger means it wants to react. Weaker means it won't react as much. So a strong acid means it's going to react. That hydrogen is going to pop off. A weaker acid means it doesn't want to give up the hydrogen. But the conjugate base of that is strong and it wants to grab a hydrogen. So now we're looking at which one would have, again, the stronger conjugate base. So again, the acidic proton is attached to the same element, nitrogen, so we can't make any distinguishing point there. They're both in a phenyl ring, not distinguishing. The same resonance is available for both of them if there is resonance. Now this one has NO2. This one has an alkyl group. So remember, NO2 is electron withdrawing, so it's going to remove electron density from the reaction center. Whereas the alkyl group, it's not going to remove, it's not electron drawing, it may even pump a little electron density into the reaction center. And so the one with NO2 is the stronger acid, because it has an electron withdrawing group. The one with the isopropyl group is the weaker acid. And so since it's the weaker acid, it's going to have the stronger conjugate base. Again, stronger conjugate base means it wants to, when it's in this conjugate base form, it wants to acquire a proton so that it becomes a weak acid. Stronger acid means it wants to give up its proton to become a weak, stable conjugate base. If something is weak, it's stable. So when we talk about weak acid, it's stable. Strong acid, reactive. It wants to get rid of its proton. Weak conjugate base, stable. Strong conjugate base wants to acquire a proton. It's hunting. So here we have a bunch of different examples. We want to know which one would be the strongest acid. So we look here. All of them have an oxygen attached to the acidic proton. That's the first thing. Second thing is do they have any resonance? Well, A doesn't have resonance. We can get rid of that. But B has resonance. C has resonance. D has resonance. E has resonance. And F has resonance. Now, C has this alkene right here, in addition to the acid. D has this electron withdrawing group. E doesn't have any electron withdrawing group or double bond. And F has electron withdrawing group in a different position. So now if we look at 2 and compare it to D, E, and F, the double bond, yes, it can probably resonate out the double bond. You could have maybe a little bit more resonance in this structure. However, when you have an electron withdrawing group, it removes electron density away from the reaction center. And so those are going to have more of an impact. So we can go ahead and get rid of this one. Oh, I forgot B, but B is electron donating, so it's going to put a little bit of electron density back in. So we can get rid of that one. E doesn't have any groups. Get rid of that one. So now it's between D and F. Again, the closer the electron withdrawing group is to the reaction center, the stronger the acid is. So the stronger the ability of that electron withdrawing group to remove electron density. So this would be the strongest acid out of these. And so which one would have the strongest conjugate base? So strongest conjugate base means weakest acid. So out of all of these, which one is the weakest acid? Can you pick it out? That's correct. That would be pentanol. So pentanol's conjugate base would be the strongest out of all of these, because it doesn't want to give up its H. But pentanate, which is the conjugate base, is actively looking for a proton. And this is just something I wanted to throw out there. So we want to know which of the following can be classified as a Bronsted-Lowry base. Select all that apply. So Bronsted-Lowry bases means that they can accept a proton. So if we look at the first one, benzoic acid, can it accept a proton? And the answer is no. There's nowhere for it to accept a proton. If we go to B, is there somewhere where it can accept a proton? The answer is yes. The nitrogen has a lone pair. It can accept a proton. So that's a Lewis Bronsted-Lowry base. A Bronsted-Lowry base, yes. Next we have acetic acid. Can it accept a proton? The answer is no. And then I put benzoic, oh. And now we have, I believe this is benzaldehyde. Can it accept a proton? Well, no, it can't. And then we have oxalate anion. I believe that's oxalate, yeah. And it can accept a proton because it has a negative charge. So there are two general categories of Bronsted-Lowry bases. These are, organic nitrogen compounds. For example, amines. Or anions. Those are the two most common types of Bronsted-Lowry bases, because all of them can accept a proton. And this is just to kind of conclude today's lecture to get you ready for next lecture. But we have all these inorganic acids. We want to know which of the following is the strongest acid. So we have HF, HBr, H3N, HCl, HI. Now you'll notice here that HF, hydronitric acid, are on the same period. So between HF and H3N, since they're on the same period, the non-hydrogen element, you got to look at the electronegativity. So HF would be a stronger acid than H3N. So let's go ahead and mark off H3N. Now what we have left is HF, HBr, HCl, HI. Now here I'm going to give you a term that you should have remembered from the very first chapter. And that is polarizability, the ability of a atom or ion to polarize the electric field around it. So when you're comparing acids where the non-hydrogen component come from the same group, that's vertical row, the one with the greatest polarizability would be the strongest acid. So here we have HF, HBr, HCl, HI. All those non-hydrogen elements are in the same group. And so what happens, what's the trend for polarizability? As you go down a group, you increase its polarizability because you have more electrons. So based on that, E is the strongest acid because it contains the most polarizable species. And next time we'll be talking about some rules to help us determine the strength of an acid. And so that concludes today's lecture over organic acids. Again, this is just supposed to be an introduction. So for example, can you name very simple, straightforward acids, carboxylic acids? Do you understand the reason why carboxylic acids have stronger intermolecular forces and hence higher melting and boiling points with comparable other types of organic compounds? Do you understand what groups you can add to an acid to increase its acidity and why a carboxylic acid is more acidic than its cousin, the alcohol? So again, that's the resonance effect and inductive effect. And then you can learn about how, and when you add, hopefully you've picked up on how where you put the electron withdrawing group affects the acidity of the acid. So on that note, we'll call it a class. And until next time, Dr. Armand signing off. So I hope you enjoyed the show. If you enjoyed it, make sure to click the like button, or if you learned something new, feel free to leave a comment. Thank you.